Hello everyone and welcome back to my channel Gyan Sampada. In our previous class of quantum mechanics, we dealt with eigenvalues and eigenfunctions of j square and jz, and also we defined raising operator. And this is the continuation class of our previous one. So if we have not gone through the previous session, then first go through it and then continue so that the result will be productive. So after studying about the raising operator, now let us move in the similar manner to understand about lowering operator. And for that, let's start our today's class. We will consider equation number 10 and operate it by j minus from left hand side. Till now we studied about j plus, that is raising operator. We understood why actually it is called as raising operator. And now we will study with respect to j minus. So considering equation number 10 and operating, we get this equation. Again we have the commutation relation of jz with j minus. Making use of it, again we can write the above equation in the form of equation number 15. And for maximum value of eigenvalue, that is mu, what we have considered, for j square we have j square ket lambda mu is equals to lambda ket lambda mu. Or when we operate with j minus, we can write it in the same form, because again j square is commuting with j minus as it does in j plus. So here eigenvalue is not going to change, but when we have the component of angular momentum, that is jz, then the eigenvalue is going to change from mu to mu minus h cross. And thus we say that j minus ket lambda mu is an eigenket of j square as well as jz, but the eigenvalues for j square is lambda, whereas for jz it is mu minus h cross. So here clearly we observe that when we have operated with j minus operator, the eigenvalue has lowered or decreased by a value of h cross, and that's why j minus is called as lowering operator. So j plus increases the eigenvalue by h cross, whereas j minus decreases the eigenvalue corresponding to z component of angular momentum by h cross. And based on this functionality itself, these two operators are named like this. And together j plus and j minus are referred as ladder operators. We know that ladder is used to either step up or step down with respect to a certain step size. And here step size is h cross, step up corresponds to j plus, step down corresponds to j minus. So the name ladder operator. And again in the similar manner, if we just go on repeating the operation, which is lowering operation, by using j minus operator for n times, then we can write the equation as jz j minus raised to n, means n times we have used the lowering operator into the wave function, that is eigenket, is equals to, we get mu minus nh cross into j minus raised to n ket lambda mu. And again here, for the validity of equation number 4, there must be a cutoff value for n. N cannot be infinity. So the minimum value of m without violating the fourth condition, that is lambda greater than or equal to m square, be mu minus nh cross. And then based on that we can write jz j minus raised to n plus 1 ket function is equals to mu minus n plus 1 h cross into this function, and this will be equal to 0. To interpret it further, since we have mu minus n plus 1 h cross not equal to 0, we can say j minus raised to n plus 1 ket lambda mu is equals to 0, because the previous equation has to be valid, and j minus raised to n plus 1 can be written as j minus into j minus raised to n. So it is something like n plus 1. And again, if we pre-multiply it with j plus from left hand side, then we get j plus into the same thing, and we know that j plus into j minus is equals to j square minus jz square plus h cross jz, and when we substitute it back and put the value of its corresponding eigenvalues, then we get equation number 16, that is j square corresponds to the eigenvalue lambda, jz square, here we have mu minus nh cross whole square plus h cross as it is, jz has mu minus nh cross. So this is without violating the condition lambda greater than or equal to m square, which is equation number 4. And here we know that j minus raised to n ket mu cannot be equal to 0. And thus, for the validity of equation number 16, the first part in the bracket has to vanish, which we call it as equation number 17. And to this equation, we will just substitute equation number 14, where we have got the value of lambda as mu into mu plus h cross. So when we substitute lambda as mu into mu plus h cross from equation number 14 and simplify it further, we can observe that mu square is going to cancel with mu square, and some other terms can be collected, like h cross mu plus h cross mu becomes 2h cross mu plus 2 mu n h cross as it is minus n h cross square minus n square h cross square equal to 0. So now we can collect the terms by taking common terms outside the bracket, and when we simplify, we get n plus 1 into 2 mu minus n h cross equals to 0. We know that n is a number of steps, so it is something like a natural number plus 1. So whenever a number is added with 1, it never becomes 0. So the second term itself has to vanish. So we can say that 2 mu minus nh cross is equals to 0, which is 2 mu equal to nh cross, and thus we can write mu is equals to nh cross divided by 2. Here n is nothing but the number of steps from the maximum eigenvalue mu to the minimum eigenvalue mu minus nh cross, and remember it also includes 0. So this is an important thing where we have found out the value of mu with respect to the operator, and here n is the number of steps from the maximum eigenvalue mu to the minimum eigenvalue mu minus nh cross, and it also includes 0 in it. And if we write j for the value of n by 2, then for operator jz, we have the maximum eigenvalue as jh cross, whereas the minimum eigenvalue will be minus jh cross. Because we know that maximum eigenvalue itself is mu. So when we substitute n by 2 is equals to j, then we can write the maximum eigenvalue mu is jh cross, whereas the minimum eigenvalue will be mu minus nh cross. Mu is n by 2 h cross, that is nothing but jh cross minus 2jh cross, that is for j is equals to n by 2. So jh cross minus 2jh cross will become minus jh cross, that is the minimum eigenvalue. And thus in general, for a given value of j, we can say that the eigenvalues of jz are m h cross, where m is taking the values of j, j minus 1, j minus 2, so on up to minus j. It is similar to that of the magnetic quantum number, that is m, which takes the value from minus L to plus L. In the same manner, here we are having m equals plus j to minus j. So minimum to maximum. And remember, n is going to be always an integer. Therefore, we can write j is equals to n by 2. That is, n is, let us consider the whole numbers 0, 1, 2, 3, 4, 5, so on. So dividing it by 2, because we have taken j for n by 2. When we do that, we find out the j values as 0, 1 by 2, 2 by 2 is 1, 3 by 2, 4 by 2 is 2, 5 by 2, so on. And thus we get the simultaneous eigenvalue equations for operators j square and jz as j square ket jm is equals to j into j plus 1 h cross square into ket jm, and jz into ket jm is equals to mh cross into ket jm. So here j into j plus 1 into h cross square is the eigenvalue of operator j square, and j takes the value 0, 1 by 2, 1, 3 by 2, so on, and mh cross is the eigenvalue of operator jz, where m takes the value minus j plus 1, minus j plus 2, so on up to plus j. But how you got in place of lambda this j into j plus 1 into h cross square might be the question. So if you remember, when doing the classes of hydrogen atom, we studied the particle in spherically symmetric potential, etc. There we have come across this value. So here lambda is equals to j into j plus 1 into h cross square. So whatever these equation we have got, which shows the eigenvalue and the eigenfunction corresponding to these two operators, is explained, and also how a lowering and raising operator works is also justified. So earlier we had considered lambda as L into L plus 1, because there we had taken orbital angular momentum, and now we have just considered the general angular momentum. So there L was taking the value of 0, 1, 2, 3, so on, but here J takes the value of L plus S, that is 0, half, 1, 3 by 2, 2, so on. So that is how the difference comes. And also if we look at the eigenfunction, that is the eigenket, we have denoted it as ket Jm. So why Jm? Because J corresponds to the eigenvalue of operator j square, and m corresponds to the eigenvalue of operator jz. And we know that both are linked to each other. So in j square we have the component of square of jz also. But however, their commutation relation gives us the value as 0, that is they are commuting with each other. So if we look at it, then the eigenfunction, what we have got here, it gives us the spherical harmonics, which we have already solved while solving the angular part of Schrodinger equation of a system which moves under spherically symmetric potential. So there we have the contribution of both m as well as j, or both m as well as L. That's why the eigenket is represented as ket Jm. So this is the lengthy method where we are going to justify or validate the eigenvalues and eigenfunctions corresponding to j square and jz. And in my next classes, I will be dealing with a very short way how to give the eigenvalues and eigenfunctions of L square as well as Lz. So there we will just make use of our previous basic properties knowledge, and without using any lowering or raising operator, directly we can tell what are the corresponding eigenvalues and eigenfunctions. So in these two classes we have completely studied about the details corresponding to eigenvalues and eigenfunctions of j square and jz, making use of lowering and raising operators, or we can say we have defined or we have understood the working of raising and lowering operator. So this is it for today's class. See you in our next class. Till then, stay tuned, study well, and thank you for watching.